And during the exam review, we will be going over basic concepts like Ohm's law, nodes, Kirchhoff's current and voltage laws, power, passive sign convention, independent and dependent sources, resistor networks in series and parallel, voltage and current division. And then my partner Mandy will go over the rest of what is going to be on the exam. So we will start off by going over nodes. I will draw a simple schematic, and then I'll ask you guys to see how many nodes are there.
Sorry, is this 12 over 2?
Yes.
Okay.
Okay, so should be this schematic. So yeah, just imagine that everything is connected, but you basically have 2 resistors in parallel and 1 in series with that. So can you guys tell me how many nodes would be in this circuit diagram?
Let me count. 1, 3.
3. Okay. So do you know how I got 3, or should I just go? I'll just go over it real quick. So the first one would be from here to here, or like that. Second one would be from here to here. And the third one would be from here to here. I'll just number that. 1, 2, 3. Okay, so that's basically how you find the nodes. And a node is basically a contiguous region of a circuit. All points can be reached without jumping over any component. A node has 1 voltage, and a node may have multiple currents entering or leaving the node. So that's basically it for nodes. And then we will go over independent and dependent voltage sources and current sources and the symbols that we use for those signs. So when you have an independent voltage source, you draw it with a circle. And if you have an independent current source, you have a circle with an arrow in it. And then basically you have the eye. And this is independent. Right, like that. Dependent is a diamond with the plus and the minus with the voltage. Dependent, and for current, oh wait. That's how you do a dependent current source. It's basically a triangle with a arrow in pointing to the direction the current will be going in. How do you scroll down on this? Indeed. How do you go down?
I think that's that they give you for the space.
Okay. Mm-hmm.
Oh, that's right. Oh,
Yes.
and then try that.
Okay, sorry for the technical difficulties, but I'll just erase everything and then we'll continue. Okay. Next, we will then go over Kirchhoff's current and voltage laws. So, but before that, I think it's better. Before we do that, I think it's better if we just go over Ohm's law, which is V is equal to IR, and then I'm pretty sure you guys know what the formula is for power, which is P is equal to VI. And then using these two formulas, you can derive many different formulas, and then I'll just go over the derivation of those formulas. So for P, you have, first you would substitute, or write R is equal to, you write I is equal to V over R, and then you would sub that into the original equation for power, which is V times I, and then you would get V times V over R, which is then V squared over R. That is one formula that you can use for power. Another formula that you can also use is, instead of deriving from V as IR, you can then get so the power formula is I squared times R. The way that you would get that is by simply plugging in the I times R for V. So yeah, that's basically how you can substitute power for Ohm's law into the power equation and then calculate different formulas that can be used for different problems. How do you scroll down on this?
I don't know. That's a good question.
Oh, okay, my bad.
Try.
It should be more space now.
You can zoom in as well, but I don't know. So.
Maybe something inside, but yeah. And then we will go over resistor networks in series and parallel. So first I'll show you how to calculate the equivalent resistance when you have three parallel resistors. So basically it would look something like this. And basically like that, you have three resistors in parallel, R1, R2, R3. And the way that you calculate parallel resistance or equivalent resistance is with the formula R equivalent, 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. And then this equation can then be simplified into R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So that is essentially how you calculate equivalent resistance if you have three resistors in parallel. Of course, you can have more resistors or just two. I'll say if you had two resistors in parallel, it would be roughly the same, but there's a little easier step that you can use. So say if you have R1, R2, the yeah, using the original equation, R equivalent is 1 over R1 plus 1 over R2. What you could also do is R equivalent is equal to R1 times R2 over R1 plus R2, which is a lot faster if you have two resistors in parallel. And a neat little trick is if you have two resistors in parallel with the same value, you can just half them, because that's the equivalent resistance. So say if I take R1 is 4, R2 is also 4, R equivalent would then be 4 times 4 divided by 4 plus 4, which is 16 over 8, and then you get 2. So yeah, it's just R equivalent is equal to 2 ohms. Are there any questions up until now? No. Okay. I think we'll move on then.
So like to make it clear, is anyone done writing? Does anyone want to like keep writing?
Does anyone still need to take some notes, or can I erase it?
You can go ahead and erase.
Thank you.
Actually, thank you.
So there is no delete option. Hello? Switching this out. So I have to click this.
So we're gonna try a different method.
Sorry for the technical difficulties. It's my first time doing this, so
You're doing great.
thank you.
Okay, so I'm gonna share the screen, put it horizontal. And can you horizontal? Yes. And then just again, you can go ahead and fix this. So before I was afraid of the echo, but it's not doing it anymore. So I'll go ahead.
So yeah, that's how you calculate equivalent resistance in resistors in parallel. We'll do series real quick. Series is, I think, pretty easy because you just have to calculate the total of the resistance, so adding them up. So say you have a resistor here, another resistor here, voltage source. R1 is 500. R2 is 300. This would then simplify down to one resistor of R equivalent being R1 plus R2, which is 800. And then say if you have a voltage source of 100 volts, you can then use Ohm's law, which is V is equal to IR. 100 volts is then I times 800, I being 0.8. If my math is correct, yes. And then that's That's how you do.
Wait, I is what?
I'm not sure if it's 0.8, but 800 divided or 100 divided by 800. I don't think the math is correct there. So yeah, I is then basically 100 divided by 800. Yeah. Does anyone have any questions until now? Going good? Okay. I think then we'll just step over to a quick problem where you have to collapse a few resistors and then solve for I. How do you clear the whole page on this?
Sorry.
How do you clear the whole page?
Clear the whole page.
Yeah.
You select that circle at the top. That's like the last one. So it's 2 spots. Yeah. And then you do the same as. And then you would click X to clear once you hit your selection.
Thank you. So yeah, I'll just draw it out for you guys real quick. We can solve. You have 10 volts here, 100 ohms, 100 ohms, 250, 500, 300, 1,000, 2,000, and 5,000. Does anyone know what the first step would be to solve this?
Are the right two in parallel? The rightmost two?
Are you talking about this one and this one?
Yes.
Yeah, those two would be in parallel. So you would first collapse those two by calculating R equivalent, which is then using 1,000 times 2,000 divided by over 1,000 plus 1,000, which is then an amount. Let me just. Okay, your R equivalent from that will be 666.67 ohms. You would then have a new circuit that you would have to draw, but I'll just draw the right side of it. So you have this resistor right here, this. So the 666.67 ohm resistor would come here. The 5,000 right here, and then you would have still 500 and 300 over here. Now, what would the next step be?
2 in series on the right.
Yes, which ones?
5,666.
That's correct.
And then while we're at it, you could also add the 2 in series on the left.
Yes, good job. So you would have a 800 ohm resistor here. Does everyone get how we got that? Okay, good. And then another resistor over here, which would be 5,600. 7 ohms. It's pretty simple, I think. Then what would be the next step, right? Yes. So you have 100 here.
It would be simpler to do the 800 and the 200 groups together, right? So you get a better number. the beginning.
That is correct. You can do all three at once.
Yeah, you can do all three at once, but that's not fun.
Alright, let's scroll down.
Just use like take off fingers.
Okay, yeah. So then you calculate R equivalent. So 200, or yeah, you didn't then do what you said. First calculating out the 200 and the 800 ohm resistor. Which is which is 160 ohms. Then you take the 160 ohms and calculate another equivalent resistance. The 160 times 5,666.67 ohms divided by 16 plus 67. And this would then be a resistance value of 155.61. So you can then redraw the circuit and you would get something that looks like this. Yeah. Just checking if you're paying attention. So you have a 200 ohm resistor here, 100 up here, 155. Like 61 there. And what would the final step be?
Oh, it's all in series, so you just put it together.
Yes. One resistor right here, 455.61. And to calculate I, which is the original question, we use V over R, which is then 10 over 455.61. And that is then your final answer.
Can you go up a little?
Yeah.
Or worse?
I think that bottom resistor was 100 this time. We put 200 on the bottom.
That is correct. It was 200 at the start now. So yeah, are there any questions? No? Okay. I think we'll move on then to Kirchhoff's current law. We will be having to calculate the currents at different spots in the circuit. It's not scrolling down. It's not scrolling down.
Oh, that might be the end of it.
Oh.
You might have to erase.
Okay. Oh. Thank you. So yeah, basically if you have a diagram like this, you would have to calculate the current at the different spots. So here, say this is 1, 2, 3, 4. As you guys know, current flowing into a node should be equal to the current flowing out of the node, right? So you're basically calculating the current at each of those nodes. So say if you have 1 amp going there, 6 going there, 6 there. Find how much current is going there. This will be D. A. If you have 10 going up there, 12 there, 5 up there, 2 up there. B is another question. 7 leaving there, and C up here. So what would the first step be? How to solve this? I know it's a bunch of numbers. So I hope you guys can follow it. Okay, we'll first look at spot number 1. Okay. So if you look at 1, you have how much current entering the node?
6.
6.
Have D leaving.
Yes. So 6 should be equal to 6 plus 1 plus D. You can then solve for D, right?
Isn't 1 leaving because the air goes away from the node?
Yes. So if 1 is entering the node, and if 6 is entering the node, 6 is going up north, 1 is going west. So how much is going south? D is going south. But as you guys know, there could also be negatives, right? So yeah, after this simple math, we would then have D is equal to -1. So technically the arrow is like trying to trick you, and it's actually -1. Do you guys get that, or? Okay. So then you find the current at node number 2. If you have B entering it, 7 leaving it, plus C plus 6. Since you have 2 different variables in that, you would have to solve that later after finding B. Okay, so you then go to 3. What is entering 3? So you have the 10 entering plus the D due to the arrow, right? But since D is -1, you would have to have -1 here. A is also entering, so you have A there, and you have 12 leaving. So all that should be equal to 12. So, with a simplification, you should have 12 minus 9 being 3. So A is 3. Then you move on to 4. How much current is entering 4? 5 and 12, right?
Oh, it is. Which one's 4?
4 is this one down here.
I thought I was an 8.
My bad for the handwriting.
And plus we need 4 on the right.
B. Yeah, we're getting to that. 4, leaving 4 on the right would be 2 and B. 2 over here and B, right? So you have 5 plus 12 is equal to B plus 2. And this would then be solvable, right? So for B, what would you get for B? 15, okay. Using B, you can then solve equation number 2 up here. You get 15 is equal to 7 plus C plus 6. So what is C? C is indeed 2. Are there any questions? Yes.
just to make I read correct. So for node 4, 12 and 5 are entering,
Yes.
and then going east, that's 2, right?
Yes.
Okay. I didn't see.
You're good.
Oh,
Is that clear? Good. Okay. Then we will move on to Kirchhoff's voltage law. So plus minus. So say that 16 volts, 10 volts, 7 volts. And this is A, this is B. So as you guys know, when you're finding the voltage over the resistors using Kirchhoff's voltage law, you have to look at the loops, right? So how many loops would this have? 3, yes, 3 possible loops. So you could solve for B using 2 different ways and A 1 different way, right? So what do you guys want to solve for first? A. Okay, we'll solve for A first. And remember, when using Kirchhoff's voltage law, you have to pay attention to the signs of where you start from. So we will start from here at the top of A. So you have positive A minus 16 because we're going in that direction. So you enter from the negative side. So it's minus 16 volts.
Wait, it's a 16.
That is a 16, yes. And then you have a plus here, so it is plus 10 volts, which should be equal to 0, right? So what would A be? A would be 6 volts. So using A, you can then easily find B, which would then be starting again from the same from A. Sorry, from A, you would have 6 plus 7 minus B is equal to 0. So
We're starting from A, right?
yes.
Oh, and we're going downwards instead.
Yeah, you're going downwards again. So 6 plus 7 minus B is negative B is equal to negative 1. B is then 1 volt. You guys get that?
wait, hold on. So you're starting at the top of A, right?
Yes.
So you go down.
Oh wait, no.
Yeah, it's at a 13.
Yeah. 6 plus 7. 13 volts.
It doesn't matter what direction you go in though, as long as you're consistent with your sign.
Yes, just pay attention to the signs and then you should be good.
So in theory, you could do it upwards as well.
Yeah. So you could also
do 6 plus B minus 7.
yes.
Wait, but you have to do minus.
Oh wait, yeah, it would be minus 6 because you're going the signs are changed.
Yeah. So if you want to double check your answer, you can always like go a different loop as well. And then if you start say here and use loop 3, which is around the whole circuit, you would start at negative 16 plus 10 plus B minus 7, which is 0. And you get B is equal to 15. So that's a different way to double check your answer. So like I would have seen that I thought 1 is the wrong answer. And then I will go over the formulas for voltage division and current division. So for voltage division, the formula, who knows the formula for voltage division?
Then V total times the resistance over R plus R2. Total.
VT equal to R2 over R1 plus R2.
Yes. So V total of V total times R1 over R1 plus R2 is equal to V out. So say if I have a simple circuit like this, $12,000 for R2, R1 is 7,000, 10 volts here. Your V in, which is V total, will be 10 volts here, and then you're trying to find V out, right? Say over R1. So plugging that into the formula, you have 10 times R1, which is 7,000, divided by 7,000 plus 12,000, which is then, yeah, that should be how you find V out.
70,000 per day.
Yeah. Are there any questions?
So if you have 3 resistors, just add the third one, right? To the bottom one.
I'm pretty sure that you can only use voltage division for 2 resistors.
No, I think it's just as long as they're in series.
Yeah, as long as they're in series as well.
So only 2? Or I can do more than 2?
I think only 2. And if you want to double check your answer, you can always just add these 2 resistors in series, calculate the current, and then do the current times each resistor to find the voltage over them. So there are always ways to double check your answer, which I would advise you to do. Next, we'll go over to current division, and I'll just go over the formulas for that. If you have IS, I source, you have a resistor there, which is I1 over R1. I2 over R2. So the way that you calculate I1 is R2 over R1 plus R2 times I source. And I2 would then be R1 over R1 plus R2 times source. So yeah, that's basically how you do current division. So these are very important formulas that you should remember for your test. You can always just work back and solve your answer. But that, I think, concludes my part of the IEEE review, and Mandy will take over. Thank you guys, and good luck.
That's the wrong slide. So my name is Mandy, and I'll be going over the second part of the first IEEE tutoring review. So this is where the next portion of the review is going to start at, where you go into sinusoid notation, all of the phasor math, and then inductors and capacitors, and then DC and AC and circuit analysis. Can y'all hear me correctly? Okay. So we've seen sinusoid notation in a lot of different problems, but now's the time to really dissect which part means what. And so we have a voltage signal here, I call it VT, and we're breaking it down into its parts. So who knows what this part is called? The VM.
Right there, you say use amplitude.
Oh, yeah. So that's amplitude. And then how do we get the peak to peak voltage?
Oh, I think I don't know. That's on here.
Oh, okay. So the peak to peak voltage is not amplitude. It's going to be double amplitude. So let's say you have a sine wave, right? It goes like this. This is one period. This is the amplitude. Let's say it's at 5 volts. And this is Vm. But what's the peak to peak voltage? It's going to be double amplitude. So it goes from this peak down to this peak, which is going to be 10 volts. 5 volts up and 5 volts down. So we often denote that as V and then subscript PP. Peak to peak voltage is 10 volts. And then we have, for the next part of our sinusoidal wave, it's going to be the angular frequency, which is 2 pi your cycles per second, frequency in hertz. Okay, and then T is for the time. So you see how these two components, the angular frequency and the time, they're inside the argument of sine. So the angular frequency is radians per second, that's the unit. Time is usually in seconds. So double or omega times T leaves you with radians, which is what we often find whenever we're trying to put something into a sine argument, right? We put it in either degrees or radians. Okay, and then we said period is 2 pi over the angular frequency, and then frequency in cycles per second or in hertz, which we often denote that as F, is 1 over the period, T. So that's all the components for this signal here. But then we have another signal with a phase shift, which is this symbol. And then it's going to be in degrees or radians, usually degrees. And what's important to do in a lot of these applications is converting from degrees to radians or radians to degrees. And you just have to know that 180 degrees is pi radians. Now we're moving on to the complex numbers. So we're trying to convert rectangular coordinate system to a polar coordinate system. So we often see rectangular as like x, y, and then let's say you have a point at x equals 3, y equals 4. Oh, you have a question?
Yeah, could you go back up to like the period equations and stuff? I didn't quite get it.
Oh yeah, sure. Oh yeah, let me know if I'm going too fast.
You did say angular frequency was 2 pi times frequency.
Yes.
Okay.
Wait, the angular frequency is 2 pi times frequency.
Mhm.
Okay, I'm sorry, I made you repeat this.
Oh, no problem.
We're here to help, so ask any questions if you have them.
Are we good on this part? Does anyone need to copy anything else down? Good. Right now we're in the rectangular coordinate system. 0.34. Then we already know like the x and y's, right? So usually they want something that's complex numbers, because whenever we deal with complex impedances, we're going to have to do a little bit of complex number math. So that's like just the start, a little bit of an introduction, but I want to direct your attention to these formulas here. So for me, I don't usually like memorizing, but for this one and for this exam, it was really helpful for me to memorize this one in the pink and then this one in the purple. The one on the very right is just prefixes, but these two ones are really useful for me for the first exam and then also for the rest of the exam. So if you want to take a picture of what's on the board, you can. So the pink is converting between sine and cosine, and then the purple is converting between time domain and phasor domain. You good on this part?
So if you're going from time domain to phasor domain, you just subtract 90 degrees if it's sine, right? You get the same if it's cosine?
Yes. Okay, so back to the complex number math and converting between rectangular to polar. So we have something like, let's say your output z equal to x plus jy, where y is the imaginary component and then the x is the real component. So let's say we want to turn that into something that's polar. So here we want to convert between these two. And so the first part of the polar is magnitude, so r is magnitude. And then this is, as you remember, phase. So how we get magnitude is we do the x squared plus y squared, which is basically just derived from the Pythagorean theorem. And then we get the phase by taking the inverse tangent of y, so the imaginary component, and x, the real component. Then when we want to switch back from this polar to back to rectangular, and we want to get the x and y's again, we take the magnitude, multiply it by cosine of, this should be the same as the symbol for the phase. Yeah. Any questions on this part? Nope, okay. So you have all done like some of the phasor math in the previous homeworks. So let's say you have like a 6 plus 3j minus a 5 minus 2j. And these subtract like normal, right? So what should the answer be for this operation?
1 minus 5j.
1 minus 5j. So with these rectangular formations, or not rectangular, but you know what I mean? These addition and subtraction work really well with when you have them in this form. Well, what about multiplication and division? No? You'd have to convert it to polar.
If you wanted to, can you do the FOIL method if you wanted to?
Foil, I guess you could. Yeah, you could still foil with these, but it's just easier and will save you a lot of time if you convert to phasor. Then if you keep it in this format. But you can still FOIL distribute that kind of thing, but it's just, it gets really messy at that point. So for multiplication and division, you're going to want to convert to polar. Then we have these extra operations here, where you have square root. And then when you have square root and it's in already the polar form, you just take the square root of the magnitude here, and then you divide the phase by 2. Y'all know this symbol? What does that mean? Complex conjugate. So basically, you're going to want to take the opposite of the sign that's in between the two components. So if you have x plus jy, the complex conjugate of that would be x minus jy. And then vice versa, x minus jy, complex conjugate is equal to x plus jy. If you have it already in the polar form, you'll just keep the magnitude the same, but the angle is the opposite sign. Then we have the reciprocal. So 1 over your, whatever you're measuring, is going to be 1 over the magnitude. Since we're going to try to have it in polar already, and then the angle would be the opposite sign here. A lot of people had questions about whenever they would do like the complex math, and then they would get their final answer on McGraw-Hill. It would mark their magnitude right, but the degrees or the phase is wrong. And so, do you have any ideas on why that could happen? Has that ever happened to you? Yeah? So what happens is, whenever you do tan inverse of something, you're getting the reference angle instead of the actual answer that you want. So let's say you have something that's like, I don't know, 3 minus J4, and you're wanting to turn it into the polar form, right? So whenever you take the magnitude, that's easy, right? You just do 3 squared plus 4 squared, right? And you get 5. That's fine. So McGraw-Hill will mark it right. But then let's say you wanted to do the tan inverse to get this part. When you do tan inverse, -4 over 3. Then you'll get something like, you might get like, or
-53.
-53 or something like that, right? Degrees. But that's not your answer, right? Yeah, that's a little bit hard because that's not actually what they want. Because in order to make make tan inverse a function, they kind of restrict the domain. And then whenever you put in the thing on the calculator, it doesn't give you the right answer. So in this case, it actually does work out, -53 degrees. But whenever you have, let's say, -3 plus J4, it'll give you kind of the same thing, but it's not right. So to fix this and to get the right answer, you would have to first look at where you are at on the XY coordinate system. So you have a negative X, a positive Y. So what quadrant would that be in? Quadrant 2, right? And then negative 53 degrees is in the 4th quadrant, so you don't have the right quadrant here. This is like just a reference angle, 53 degrees. So what you're gonna do to get it into the right quadrant, which is quadrant 2. Quadrant 2 is in between, it's in between 90 degrees and then 180 degrees, because you're going this way if you're in the positive direction, counterclockwise. And so you have 53 degrees as a reference angle, which is the angle coming from the x-axis. So it's 53 degrees up clockwise. So what is that angle? It's going to be 180 minus 53 degrees. That's going to be the angle that you put into your McGraw-Hill answer, because it's the step one, and I think when you get tested, you'll have to input an angle that's in between negative 180 degrees and positive 180 degrees. Does that make sense, the reference angle thing? Okay. Okay, so now we're on to the capacitors and inductors, because we just talked about complex impedances, right? And those happen whenever we introduce capacitors and inductors into the mix. We want to make sure that we know these key things. So if you have a purely resistive circuit, meaning that your circuit is consisting of resistors as the impedance, you're going to have your voltage and your current impedance. And then if you have a purely inductive circuit, voltage is going to lead current. If you have a purely capacitive circuit, then current is going to lead voltage. And you can remember these three things by remembering this phrase, which is what she taught you. It's Eli the Iceman, so you have E as your voltage, I as your current, and then in the middle is L for inductance. And it's the same thing here with your capacitor. You want to know that at DC, inductors act as shorts, and then at high frequencies, they act as opens. Capacitors at DC act as open circuits, and they act as short at high frequencies. So at high omega angular frequency. So that's just kind of an intro. Right here I go into what capacitors and inductors are. So in capacitors, you have two plates separated by dielectric, and whenever there's a voltage being supplied, voltage deposits a positive charge on one plate and then a negative charge on the other plate. That's the same magnitude. As far as inductors, it's a winding around a coil, and it creates a magnetic field that resists any change in current. Also for capacitors, because of this time it takes to charge one plate as positive and negative on the other, that's why you have like a little bit of a lagging voltage. And then we have these two equations for energy stored. So you've seen energy stored in a capacitor as 1/2 the capacitance value, which is usually in farads. I mean, it should be in farads. And then you have the voltage across capacitors squared. For energy stored across the inductor, it's going to be 1/2 inductance. Current across the inductor squared. And then we have capacitors in parallel and series. So what happens whenever we are given a circuit and we're told to give them the answer to what the equivalent capacitance is? So let's say you have something like this. So it's 3 capacitors in series, and they want to find the Z. Let's say they're all just 1 pair. So what would we do in this situation to give them this EQ?
Is it the same thing as resistors?
For capacitors, it's the flip. So if you have,
In series, you have to do the inverse.
yeah, series, you would have to treat them as
It
a
would still be
series.
1, regardless, right?
Yeah, because I put these as like just
But if it
one.
was like 2 or something, then you have to do the whole 2 times 2 on top over 2 plus 2, which would still be 1, actually. I think.
Yeah, I mean, I just put like these as examples, but like as soon as like they ask you, they'll probably put different ones, right? So it would just help to know that here you would treat them as if they were resistors in parallel, and if these were actually in parallel, you would told to find the equivalent capacitance, you would treat them as if they were in series. So if this was 2 farads and this was 2 farads, it would be 4 for ZQ.
For inductors, we treat them the same as we do resistors.
Yep, inductors would be the same as resistors. Now we can work on some practice problems. So, so for the phasor math complex, like that complex math, do you want to go over an example of that? Okay. I have the problems written in a thing that I had beforehand, so I'm just finding where it is. So let's say we have equal to 12.25 plus 18.21J. Then we have Y minus J. Then we can do X times Y, and then we'll do the complex conjugate of X minus Y. Okay, so what should we do first for part A?
Convert to both.
And how do we do that?
So find R, square root of 12.45 squared plus 18.2 squared.
that 45, right? It's 45, right?
12.45.
22.06.
22.06 for our magnitude. And then for our phase,
It's like 10. Okay. Oh, it's 55.64.
do we have to adjust this? Good, good, good. So you're gonna write it as 22.06. This is X. Now for Y, we'll just do the same thing.
So let's say 8.02, right? Or that one?
Oh, it's an 8.
12.34.
Then for our angle,
Negative 49.47.
do we have to adjust or no?
No.
Very good, very good. So negative 49.47.
47. That's around it.
Then we'll just do the same thing, write it the same way for Y. And we're trying to multiply, right? So now that we have X and Y as their polar forms, how do we multiply them?
You didn't go over that. Really. I forgot to ask that.
Oh, sorry.
I forgot to ask that. You just said if it's multiplication or division, go to polar, and then if it's reciprocals, and I forgot to ask that.
Oh, sorry. So for multiplication, you're going to do your magnitudes multiplied. So in this case, it's 22.06 times 12.34. Then for the angle, we add them. So it's going to be 55.64 plus negative 49.47.
You did 272.22 for the magnitude.
Then for the angle,
6.24. So you did say subtract, right?
Add.
yeah, because since this is a negative, I
Oh,
just put it as,
Yeah, it was 6.24.
that's correct. Any questions on this part? Good on this part? Okay. For division, you would do the same, so you would divide X by Y. And then subtract these two. So it would be 55.64 plus 49.47 in the end. This is for, we asked for division. Okay. Then we're gonna do the complex conjugate of X minus Y, right? So X minus Y, do we need to convert to polar? So what should we do first for this one? How do we subtract X and Y?
You just subtract the subtract.
Then what do you get for the final answer?
You get 4.43 for the first one.
Then for J?
27.69.
What's the complex quantity of this?
Minus 27.
And then if they ask you to convert it to polar, you know how to do that, right? Okay, so that's for the complex math. So we already got these cards finished for complex math. Now let's try to do the conversion, because I know that's one of the topics to cover. So let's do a practice problem on converting from time domain to phasor domain. So for A, we want to convert that to phasor domain. Then you would use the table that you took a picture of to see how we do that. So any ideas on how it should be done?
50 equals 60.
Then how would you get that from that table thing?
Sorry, what?
How would you get the 60 degrees?
Oh, if it's signed, just subtract 90 degrees.
So he got that from the part of the table that said that for the sign in time domain, you would take the phase shift and then subtract 90. Now for B, what do you think it should be?
50 angles to -70.
And because it's cosine, you can just take this angle and just transfer it here. You don't have to do any changes as far as when you convert it to phasor domain. Does that make sense? And then this part, the part that goes in front of it, it's always gonna be the same here since it's magnitude. So this is amplitude and then this is amplitude. Then for C,
Is it 80 angles here?
A at 0.
Can you write 360 instead of 0 or no?
I guess, because they're like the same, but
It doesn't like it though.
it doesn't like it because it wants you to do from negative 180 to 180 on the software, the McGraw. Usually, I don't know if that changed. Did that change? No. Okay.
You guys use connected fundamentals one when you just have
Fundamentals 1 now. Fundamentals 1 is a lab class, so you don't really use like any homework platforms.
So this is the only class where we have to use connected, right? Because I paid for just this semester.
I mean, okay, so maybe if like there might be an ENA professor that does it. I'm not like completely sure though. I'm not completely sure, but there might be some professors who use it. And if you have to take something like discrete math, they might use that too. So it depends, but for fundamentals, since it's just like mostly a lab class, they don't use any like homework software.
Didn't miss much. Oh, yeah, you did. Yeah, a lot.
So it's recorded. So for D, ideas.
Just like eights.
Set the angle of 35, right? Oh wait, okay, so that should be minus 90.
45.
Yeah, it really helps to memorize that table of things. Okay, so we good on phasor, time domain conversion. And we have, oh yeah, these impedance formulas, I don't think I wanted that. But for the impedance of an inductor, it's going to be J omega. And then we remember omega is 2 pi regular frequency, right? In case they give you something in hertz, and then you have to calculate impedance. For the impedance of a capacitor, it's going to be 1 over J omega C, or you can write it since 1 over J is equal to omega J, you can write it as negative J over omega C. Negative J over omega C. Yep. And then I believe she may have had y'all do like the complex impedances, like where you do complex impedances and like the equivalent, like ZEQ of a circuit. That's like you have your voltage source in AC, and then you have like resistor, capacitor, inductor.
But it's just a resistor problem.
It's like, did she have you guys do something like let's say you have source, you have capacitor here, an inductor, and a resistor. And then you have to find ZQ, and then find IEQ. Did she have y'all do that?
Maybe briefly, so yeah. That's not. But it's just like the resistor network problem. Except with impedances instead of resistances.
Yeah. Did she have y'all do it in parallel?
I don't remember the concept. I think we went over it like a little bit, not a great detail.
Let me check to see if that will be on your example one. Because that might be the next lecture. I'm not completely sure.
I think you get over it, but it's like.
Well, before that, we can do a energy example. So we can do just a quick energy stored in capacitor, for example. I'm like completely going ahead. Let's say you're given a 4 microfarad capacitor. And then you want to find the energy stored at times t equals 2 seconds, t equals 8 seconds, and t equals 20 seconds. So let's take a cost capacitor. Are you guys finished copying it down? So how should we go about finding the energy stored at these 3 timestamps? So let's start with t equals 2. How would we find the energy stored at t equals 2 seconds?
You could plug it into the second move. So it would be 2. 2 seconds is the less than or equal to the time greater than 5.
We have an energy stored in a capacitor equation.
Oh, that, yeah.
So we would kind of have to plug the time into here, the equation for VC, and then plug VC into our energy stored equation. So our energy stored is going to be 1/2 capacitance times VC squared of T. Okay. So now that we have that equation, how can we find what the energy stored at T equals 2 is?
Just find the VC first, VC squared first, VC squared.
So you said that VC at 2 is equal to 2, right?
Yes.
And then VC squared is 4.
Times 2 divided by 2, that would still be 2.
So it's going to be 1/2 times, remember the capacitance, we have a 4 microfarad. So 4 times 10 to the power of -6, because micro. So 1/2 times capacitance times VC2 squared, 4.
Make sure I'm understanding this right. It's for the farads, it's 1/2 times 4 nanofarads, which then converts on the bottom equation, 1/2 times 4 times 10 to the power of -6 times 4, or am I missing something there?
It's times 4. And this is micro, because it's 4 microfarads, so it's 4 times 10 to the 6. And then we said VC squared is equal to 4. So that's why we're putting it here. Since the equation 1/2 times capacitance is 1/2 times capacitance times VC squared.
Sorry, class again. Where did you get the VC originally? Or
So this is given. This part, it's a piecewise equation for VC of t, where
the time is given, right? Not the.
all of this is given. And so is the value for the capacitance.
Oh, so all we just did is use the equation t over 2 plus 2.5, and we inserted in the VC, right?
So we use this, we're at time equals 2 seconds. We're gonna use t, which is in between 0 and 5 seconds.
Substituted, put t is equals to 2 squared. Okay. Okay, so we did that.
And then for 8 seconds, you would follow the same process, but since it's 8, it's gonna be in between 5 and 10 seconds. So then you would use t over 2 plus 2.5. Okay, so we did this, we did the energy stored equations, and we did parallel capacitors and parallel inductors. And then we can do an energy example for DC analysis. We're going to spend a little bit more time on DC because it can get kind of confusing for people. Is it okay if I erase this now, or are you wanting to? Okay. finish copying? Okay.
Is that high?
Yes, I am. At the top.
Approaching 6, 8. What is H mean?
Henry's, it's the unit for inductors. So once you define 3 things, or 4 things, the current across the inductor, VC, which is the voltage here, and then energy stored in the inductor, and energy stored in the capacitor. Since this is in DC, the circuit is in DC, what do you think we should do first? Any ideas? What do we know about inductors and capacitors in DC conditions?
Show the inductors like closed.
Inductors make a short. So
And when you mean short, that means they're basically not there, right?
it's just a wire.
Okay.
This is open wire. It's just like an open wire, right?
It's closed wire. So
Short circuit means that, like, no. What is it? Just excuse me. No current is going through it, right?
short means all the current is going through it. There's no resistance, 0 resistance. Open means there's infinite resistance and no current passes.
Open circuit is infinite resistance. Short is flowing through it.
Is another word for short closed? Or no? 2 different things.
Maybe, I haven't heard it said that way. Have you heard it said that way, Laura? Shorts, do they call it closed?
Like, can you use it in the same concept?
Short circuit, closed circuit?
I always heard short circuit.
I would go for short in case like they ask you that question. And then you have to like fill in the blank. I would just say short instead of closed or any other terminology.
But you should check with your professor. Most of the higher level classes use short circuits.
Mhm.
But each professor is different.
So now we know what the inductor does in DC. What does the capacitor do?
It's open.
Okay, this was on 600, just in case, because we don't want to lose the values. And we'll do it. Any ideas for what we should do first now that we have the DC conditions covered?
Simplify the parallel of 10 ohms and 2 ohms. So just put them 1/10 plus 1/2.
I don't know what this is, so if you have a calculator, the 1/10 plus 1/2. We should get REQ is equal to
1.67.
1.67.
Yeah.
we have the equivalent resistance here. So what should we do to get IL?
Multiply the 5 amplitude times the resistance, 1.67, which gives us the total voltage.
Oh yeah,
Voltage is equals to resistance times. Sorry, voltage is equals to resistance times current, right?
yes, Ohm's law.
Yeah.
So then that's something. That's a value.
8.35.
Ideas for IL.
What does spell stand for?
It's gonna be, so IL is current across the inductor. Usually L is denoted as inductor. So we want the current across here where the inductor used to be.
We do have the voltage and we do have the current. Voltage over current will just give us a resistance, which is what we're looking for. Current. 8.35 divided by 1.67. Would that give us the current
That's
going
fine.
through the inductor?
What was 1.67? That was REQ. So if we do Ohm's law is B equals IR. We want to find IL, right? Or wherever the inductor used to be. So we want voltage, the voltage that we calculated, right? And then we're trying to find this I part, right? What's the resistance value that we can divide?
1.67, that'd be the total of the parallel circuit, would it not?
It would be, so if we did V over 1.67, or
This back to 5 is
it go, sorry?
Where you go back to 5?
Yeah, so it would give you a total, because you're doing total voltage over a total resistance. But these aren't the same, so 5 amps isn't the same as current across the inductor. You know why? So you have a current going here, and then what do currents do whenever there's a parallel circuit? Do they split, right? So
2 subtract and 1 adds, right? 2 subtract to go out of the circuit, and 1 adds, kind of like a clash. I don't remember the actual term. I think I have it
You
around.
get the voltage of what you got, subtract that by the current. So you got
it might help to just ignore this part. So that part usually messes me up.
Kirchhoff's current law. That's the law I was thinking of. Was it not?
Yeah, for currents here, because you have a parallel circuit now that the capacitor is gone, and then there's this wire here going across. You have essentially just this left, and so you just have a current and then 2 resistors in parallel, and you want to find the current that goes through here, right? This wherever the inductor was, phantom inductor. And what do we know about, so let's pretend this inductor was here, but like it's actually not. What are currents whenever there are components in series? It's the same, right? So the current across this component or this wire is the same across the current going to the 2 ohm resistor.
So we do 8.35 divided by 5.
Divided by 2?
8.35 divided by 2. Because,
Yeah, I see.
Is it because you share the node? Because if the inductor were still there, it'd be sharing the node with the inductor and with that. No, but it
The inductor is there, but it acts as it's not there DC circuit.
right. But why is it 2?
Because 2 ohms is the resistance. The resistance of that is the resistor right there.
The current keeps flowing because of Kirchhoff's current law up until it reaches 2 ohms, which then would give us the current from that entire node. Is that right?
so essentially, you have this current IL, right? And then you have the inductor and then the resistor. Yeah, so you're right about the splitting part. It does split because currents split whenever there's a parallel connection. And then once that current splits, this IL goes in this direction. Then it has to go through the inductor and then the resistor, right? And components in series share the same current. Components in parallel don't have the same current. So this is why we said that the voltage, say the voltage here was 8.35, right? That's why we said that the voltage divided by 2 ohms, this resistor, is equal to IL. Because voltage also, whenever there's components in parallel, it's the same voltage. So the voltage here at point A is the same voltage here at point B, is the same voltage here at point C. So that's why we can still use the 8.35 volts, but we use, whenever we're trying to calculate the current, we use this as the reference because it has that series connection with the inductor. So does that make sense why it's 8.35 over 2 ohms?
I'll probably just need to check back on the textbook for this. I'll just give a quick review, you know.
It always helps to just like look through it before the test. Y'all's test is on this Thursday, September 21st, correct?
Is the test hard?
It depends on who you ask, but I think I have faith in y'all, so y'all will be able to get through it hopefully with 100.
So you did say current across the components series is the same.
Mhm.
And you said also voltage.
Voltage across series gets divided. That's why we have the voltage divider formula.
Okay.
And then as Adil said with the current dividers, you use it whenever there's a current and then the components that are going to receive that current are in parallel. The voltage division formula are,
So you could use current division here.
yes, this is essentially current division. But yeah, I just wanted to highlight that the inductor IL current is going to be the same as the current across this 2 ohms.
So if I were to use voltage division, because I'm just trying to find like the simplest form so it's less taxing on the end of the test. If I were to use voltage division, then I just put it as 8.35 plus 2 ohms over 10 times 2, right? Or did I get that reverse? I'm still trying to memorize it, so my memory might be a little bit shoddy.
With this one, I probably wouldn't go for the voltage division because, like, as you have here, there's like not anything in the series. we just have parallel whenever we put into account the fact that the inductor becomes a short or wire, and then the capacitor results in an open. So it just results in this series connection. So voltage division wouldn't apply here, but if you had something like 5 volts, and then you wanted to find the voltage across each component of, let's say, a 10 ohm here and then a 50 ohm here, if you wanted to find the voltage across this or the voltage across this, then you would use a Dul's voltage division formula that you put. I think it was V source times R1 over R1 plus R2. Where R1 is the one you're trying to find. So if you wanted to do 10, you would put 10 as R1. If you want to do 50, you would do 50 as R1.
Okay.
And then since we have the VC and IL, we can use those to find the energy stored in the inductor and the capacitor. Because as we remember, it's 1/2 capacitance. 1/2 inductance. Well, since time doesn't matter, it would just be.
WC stand for again?
Energy stored in the component. So if it's WC, it's energy stored in the capacitor, and WL is energy stored across the inductor.
Inductor, you said. If it's WL?
Mm-hmm. And you would plug in the values, because we said we had these values, 6 henries, 4 farads. 6 henries would go into the equation for the inductor, 4 farads would go into the equation for the capacitor. So after the part where you get VC and IL, the rest is just like the plug and chug into those equations.
You said inductance is in henries?
Yes. So inductors, the unit is henries.
What's the other one?
Capacitors, it's farads. So henries is H. Henries. Capacitors is F, which is farads.
This might sound like a bit of a random question, but I was just wondering, did you have like any method for you to memorize, I guess, these formulas for you just to do them like that? Like any method, or did you just do it so many times that it just became habit at that point?
Yeah, after so many times, you kind of just remember, like, had like all these formulas, like the energy stored in capacitor, energy stored in the inductor. As you're like continuing to do these homeworks, there are some homeworks that she'll have where it's just like review homeworks, where there are some questions from past homeworks that she'll make you do, and then it's just as a reinforcer. So we have about 10 minutes, so if there are any more questions, I can take